quite honestly, mathematics wasn't going to become modern till the 1800s. Everything from negative numbers to irrational numbers was rigorized only then. Remarkably, mathematicians moved mathematics well beyond the Greeks before the 1800s. Descartes came up with his analytic geometry, which married classical algebra and geometry. And Fermat analyzed Diophant's number theory. Descartes came up with his analytic geometry by solving ancient Greek problems. He saw that algebraic equations have their roots at the intersections of lines. Fermat also worked on analytic geometry. He also solved maximum and minimum of curves problems, hinting at mathematical creations that Isaac Newton was to solve. Isaac Newton, of course, came up with his inverse square law of gravity. What doesn't get said very often is he derived the Kepler laws of planetary motion from his inverse square law. He also solved mathematically for the first time the precession of the equinoxes. He created calculus to solve these problems. To solve the Kepler problem, he had to show the center point of gravity. That the attractive force of a given sphere acts as if everything concentrates at the center of a sphere. He likewise did this for an ellipse as well. Isaac Newton also accomplished some experimental feats. He used a prism to break up white light into a spectrum of colors, and he invented the Newtonian telescope. Newton also solved the binomial theorem in order to make his calculus work. Newton's calculus was not like today's calculus. Today's calculus was more like the continental mathematician's calculus, that of Leibniz, the Bernoulli family, and Leonhard Euler. Mathematicians mostly explored analyzes, the mathematician's word of the calculus and generalizations for the next 100 years. They would develop differential equations, complex analyses, and the calculus of variations. Laplace would write his Celestial Mechanics, which would go to 5 volumes, 1,000 pages each, of the system of the world, as Newton had one small chapter on. Lagrange would write his Analytic Mechanics, where he used his invention of the calculus of variations to deduce the whole of mechanics, both solids and liquids. He expressed the laws of mechanics as stationary points, like min, max. The amount of mathematics generated with the 1700 mathematicians alone buries the Greeks. But they would dwarf even this output in the 1800s. They would develop elliptic functions and generalizations beyond that. The complex analyses of elliptic functions would lead to Riemann surfaces, and from there to topology. They'd use complex analyses to solve real analyses, calculus of infinite series. Mathematicians would solve number theory and abstract algebra with elliptic functions. And, the 1800s are when the number theory and algebra really advanced. Algebra didn't advance much after the Cardano-Ferrari solutions of the general third and fourth degree, back in the 1500s. Mathematicians couldn't solve the general fifth-degree equation. Abel and Galois proved the general fifth-degree equation was not solvable through algebraic means. In so doing, Galois, for one, came up with abstract algebra, group and field theory really. Galois theory is how groups and fields work together. Ring theory came out of number theory. Mathematicians would use the new higher analyses of elliptic functions to solve the fifth degree and higher equations. They'd also solve the number theory of quadratic reciprocity. The invention of abstract algebra cannot be overstated. Like the non-Euclidean geometry discoveries around the same time, mathematicians were able to come up with alternative geometries and algebras. They could change the properties that are possible with new different algebraic and geometric structures. Then, mathematicians conquered infinity itself. As already noted, Galileo noted that the even or the odd numbers could be paired with the natural numbers, and hence, the even or odd numbers could be equally infinite to the natural numbers. But then George Cantor showed higher infinities. He showed one cannot equate the real numbers with the natural or even the rational numbers. Mathematicians came up with all this before they really even became comfortable with negative numbers, complex numbers, and irrational numbers. Numbers would be defined by set theory. They were to show they can derive each number system from the prior number system. They could derive the negative number integers from the natural numbers, the rational numbers from the integers, and the real numbers from the rational numbers. Weierstrass would come up with his rigorous definition of a limit after all this mathematics was created. But I really wanted to take you up to this point to show the sheer extent of mathematics. If mathematics is as Jacob Bronowski points out in his Origins of Knowledge and Imagination, then it is about looking past our flat Earth viewpoint. Every logical proof does this. Every mathematical creation does this. Every mathematical discovery connects different facts. If Jacob Bronowski's ideas are right, then when life arose, we became finite, we ended up with a flat Earth perspective. And, it's only by evolving, learning these mathematical discoveries that we reconnect to the universe.